So now the state is no longer a state, it's an observation. And the hope is to be able to do a lot of the same structure all over again. Go through a couple of details, but now think of goals this way. The idea is here's a robot, really happy, is really excited about being told what to do. And the idea is here's the image of basically what is desired to be like the configuration of the world. And the hope is that the robot will replicate this particular configuration and to train an agent to do this. So now this doesn't have to be state conditioned, and it would just be an image. At the very least, this ends up being really helpful. Let's say, for example, I don't know, I'm trying to put a symbol in here that says like, well, the rotation of the plate doesn't really matter. If the plate is well made, the whole thing looks symmetric. So then in state space, normally you're like the agent would be trained to force to find like a particular rotation for the plate. It's not really needed. It's something we can normally ignore. So if we can train these like this basically goal condition model to also work over representations that are invariant to stuff that don't really matter for the task, it makes the task easier to solve, and we get a fantastic representation that's probably a better way to express the state. Challenge is being able to learn these two things. We still have the probability of pass that we've talked about already. Still goals. Nothing's really changed there. Still trying to maximize reward. But the one thing that now we start to run into is, well, now this is going to compress some image model into some representation space. We may not have rewards anymore. So this makes this harder to train. This may not have rewards. The part where actually this is still nice and working with the text model is a pain is like if we completely go to a text model where we just feed in text, we really don't have access to a reward function. There's really nothing that says like if it satisfied that goal. There's definitely a couple of papers lately that will then like use another VLM and ask that VLM, did it satisfy this goal? But that's not going to be like 100% correct. And we kind of know like reinforcement learning doesn't like its reward function to be stochastic or not correct. So it may help, but it's a bit risky. But at least here, already we're starting to lose from this. So basically, as we start to make this goal representation more flexible, it usually comes at the cost of it being harder to automatically compute rewards for the goals that were specified for the agent. So let's just get into this a bit more about this representation here. So there could be our awesome Baxter arm here on the left. There's a lot of details in this image, but for the most part, a lot of them don't matter. So the real question I might ask is, okay, you can hopefully notice the same change. I hope no one is colorblind in the class. Uh, Not that that's a bad thing, but just because of my poor planning. But basically, is this thing still a puck? So just because the color of this puck changed, like the task doesn't really change. It's still this object. The task is still to probably move this object from one location to the other and figure out how to just, remove and not care about a lot of the background noise, not really care about certain changes in pixels, or most of this seems the same, even for coloring. And basically, the challenge is now this image is a really high dimensional. And actually, the task and parts of the state that are of importance for the task are really small. It's actually only about like two-dimensional, just the like location of the puck, even though there's probably 30,000 pixels. In this, the state space that's task relevant is two-dimensional. And we need to be able to learn that. So this is all about this problem again, learning a good space that goes from basically observations to states. It's always about learning a good distance space such that things are meaningful with respect to the problem we're interested in. So here in this space, it's figuring out like learning some particular blob here that is now a good place for representations or encodings that makes sense in the task space, where at least this distance is like more or less correct. Yeah, that makes sense so far? Yeah, everyone's still with me for the last couple minutes of the class? Or is it just everyone's real excited for the weekend? So then this is like learning this more meaningful distance space, noise is ignored, all this good stuff. Because really part of the challenge in just doing robot learning is learning to ignore a bunch of stuff the policy should be invariant to. A lot of this is just starting in that space as well. And maybe I'll just go with this one last example. Um, this is often called, like in the literature, comparing two things. One of them is basically you can do distance in geometry space or distance in appearance space. So if you're looking at one of these two humanoids here that are like digitally rendered, a lot of it has to do with like the importance in state space. Like we've mentioned this before, like if the goal is to train the humanoid or the atlas to walk, does it really matter how much the wrist for the actual robot is moving while it's learning how to walk compared to how much it really matters for the hip of this and whether it's actually able to walk or something like that. So geometrically, looking at the change in the hand is the same amount of distance as looking at the change in the hip, but it doesn't give probably the proper output. Instead, what this should be more considered of is a difference in appearance space, like for the whole motion. There's basically this video that is desired to be matched. And it's not really the pixels exactly that it's like most to be matched, but like that appearance of how it looks. And so for different types of problems, often it's important to care about whether or not to consider distances in that appearance space or geometry space versus appearance space. Okay. Yeah, that was already mentioned. Right. Does that make sense? Any questions? No? Good. Okay. Um, let's just stop there for now. We'll start up here next time. All right. That's good. Otherwise, yeah, have a good weekend. Again, we won't be back in class until like Wednesday, so that's like 11 or 12 days from now. Otherwise, enjoy. Great. Take care, everybody. So last time, this was actually a good place to stop so we can get back to the details. Um, the idea was basically this. We started talking for a while about goal conditioned RL. It's nice because we can specify goals. We can be able to essentially like task agents as if like, here's a goal, make this happen. And that's basically what this image on the left is here is trying to show. Human asks nicely for the world to basically instead be configured in this nice organized place setting. Instead, right now it's sort of this messy part, and we want the robot to now come on figure out like how to make that happen. But this usually means if we wanted to do this in image space instead of just state space, we have to learn a good representation. So because we want to minimize this distance here between these two, particular versions of this potential image. The thing that we don't really, when you think about it, you don't really want to care about, like if you think about the plate here, this could be at some angle, but we don't really care about the angle of that plate. I mean, maybe some of you do have like a table setting and a plate that's not symmetric, but in this case, we don't. So this is like one of the factors of the actual state that isn't actually important to complete the task. And then we're going to this whole lecture today is going to follow on like how deep this problem goes whenever we're doing machine learning. So this is going to be all about like figuring out good representations and also figuring out how to suggest good goals to actually follow in these representations such that, and eventually when, as the people tasking these robots when we're telling them to do stuff, the representation has to be better so that we know what what we're actually commanding them to do. So this is also a version of this comes into play a lot even when doing imitation learning, because in this case, you could look at a video of things that I'm doing, and I gave this short example a bit already, where if I'm doing like a walking motion and I'm moving one particular extra joint of mine right now, but you can't actually see what it is. It's really just my finger I'm moving around, but that does take up some amount of representational space when you're computing a distance between these two things. But if you look at this as just, like subtracting vector 0 from vector 1, there's going to be some chunk down here that is, the joints for my finger, and those are going to get the same amount of error in terms of like mean squared error as if like I was actually changing my hip instead. And you kind of need to get the hip right much better to be able to walk than the actual finger joints. Okay, does that make sense? Is there's often called, there's like the appearance version of trying to understand distances and the geometric version of understanding distances. This one where you just look directly at joint angles is more of this geometric view of understanding and looking at distances. And that's where I give this example of like hips versus being able to actually look at fingers. Okay. The nice part is what we want should actually exist some way or another. It's just often tricky to be able to train and get it. So there does exist some model out there that we can learn where someone gives you an image or gives the agent an image or at least maybe a collection of images, it should be able to infer what the pose is for that particular agent, given enough of that data. But this is so usually in the real world, when we're working with these images, we've only got the image data. We don't really know the pose information for other people, other things we're trying to imitate or to use them for goals. So one way to get around this, to try and learn basically this model up here, we could start by learning some variational methods. So this is, okay, maybe we can learn a representation using a VAE, learn a model that basically tries to then produce the image from some latent representation. So if there's enough information in that latent representation to describe the pose, you should also be able to generate an image from it. And then this can be trained over just some data set. Usually, well, Z here is always something, some sort of random distribution that's used to kind of condition part of the representation, at least for the VAEs, which I know are a little less popular. Well, unless you're doing like latent dynamics models for really large vision these days that use some type of latent representation, then basically figure out how to map this. So what ends up happening is a model is trained that goes from the original image basically into goes from the image down to some latent representation. And then the idea has been to learn some model that goes from that latent representation back up to the image. And then hopefully with this and a really, really big pile of data, you can end up finding some model in this representation that can work out pretty well. So this is, related if you're familiar with variational autoencoders, you can train this representation using this loss. There's a lot of other details in order to be able to train this, with some extra good accuracy and learning a good representation. But after this is done, there's really this model that takes in the original state, gives you this latent, and then you can also have another model that goes from latent back to kind of like predicted state, not the original one, but often with a few issues that happen here and there. Okay, does that make sense so far? There's definitely a couple of caveats to this. One you might notice is that the thing on the right is almost more fuzzy, partly to do with the way VAEs are trained. So they're not always the best things to use for generating images. They don't, sometimes it is a bit tricky to be able to get that latent representation. And we'll talk about some of the details. So this particular image was also borrowed from some of like the Dreamer work where they were doing like learn a bit of a sequence-based latent representation. So like here's a couple of states, then predict the next state and still be able to embed some representation here over this to learn that latent representation. So this has been used for a number of different algorithms, sometimes as for goals, which is what we're going to talk about. Sometimes it's just learning a better representation, a more compact one for doing control. And if you're Maybe if you're the flavor that loves talking about VAEs more often, yeah, you can kind of get into a whole pile of other research that's like how to get better bounds on this particular loss up here by sampling things better in a bunch of different ways. But it's not really the focus on this class. We're going to use this as a nice tool and talk more about how these different kind of representation learning algorithms are going to give us slightly better trade-offs in terms of learning a good representation for describing a task. Okay, so then part of the reason we were talking about this is, so here, it was actually to be able to generate a goal. So if we need to figure out how to train these agents to work really well over a big, large distribution of goals. One choice, we write down a whole bunch of these goals and slowly give them to the agent or like watch the robot the whole time specifying different goals. But the other choice in here, using even this VAE representation, train the VAE, it now generates images, which could be like the goals that we could give directly to the robot at some distribution. So now this is really similar to our prior goal conditioned RL, but instead of the goals being from like a uniform distribution without any real information, now we can actually generate these goals and from something that's at least a realistic distribution. Yeah. Does that make sense? Questions from anybody? No? Okay. Okay, good. Because this isn't, let me know if you've got questions. This is only going to get more complicated in the next couple of slides. But the idea is here, there's a goal, some distribution for goals. But part of the, I mean, at least one quick example for why this would already be great. So if you wanted to generate goals and they're in image space, do you think it would make sense to generate goals uniformly random in the pixel space? Does everyone like remember one of those really old TV channels or something where it was all just static noise? That's most likely what you're going to generate if you just look at it in pixel space. So you're really never going to give a goal to the agent that's like anything like our real world. Well, maybe it's sort of like some of the background noise radiation that exists in the universe, but nothing we'll probably ever ask the agent to do. So then this is really this question about, you know, it's not really a good way to go about doing this, just like generating from uniformly random space. So this is where more, like now we'll talk a bit more about like, are there even better ways to be able to sample these goals, even from this trained model, but also there's a couple of really weird caveats. So if we've got image goals, one way to do this is taking some states. Then at least we know, like in this representation Z, this is the current configuration at the beginning of the episode. So at least we know that this is somewhat, you know, if you give the robot something to do and you want to give it a goal of something to do after that, at least you can kind of figure out, provide it some goal that's not too far away from its current situation. Then at least you can maybe make some way to like grow the goal distribution over time. So this is even better than starting out from totally random noise. Okay. So this is where one way to be able to do this is kind of like reuse that VAE structure from before. And it's good because we can talk about this in two ways. If you remember, the way the VAE is trained is that latent representation is, you know, conditioned or basically constrained to be near the distribution for a Gaussian. So now we can really just sample this Gaussian distribution because we've forced the latent distribution to be like that Gaussian distribution. And then from that distribution, it generates images for what those goals represent, but also just goals and generally that it can sample and stuff that looks more like, you know, what, you know, these goals will be within the states the agent can visit. And maybe that's partly because a little bit of a step that we didn't talk about as much, sort of like where do you get the data for the VAE? And a couple of the papers will talk about what usually happens is just like run the random policy in the beginning for a little while. It collects some data on the robot. So now all of the data the VA is going to be trained on is stuff the robot can actually reach. And that's basically what I'm trying to get across here. If you're going to give goals, they should still be achievable goals in some way. The best way to do that is to like literally configure your robot and collect data on those configurations And then later you can go on and sample configurations from that so it can learn how to maybe get between those different states more efficiently. In the data, though, it might have just been like totally random in the way it was originally exploring that data. Okay, does that make sense? Okay, so there's kind of a couple of steps. You're gonna initialize this random network, collect a bunch of data, basically from that random policy network, but this is all stuff that the agent can't reach. Train a VAE for a while. This particular line is probably incredibly deceptive because there's like 4 years of research into trying to be able to train that VAE well enough to get a representation that kind of works. And we'll talk about one or two of those papers today. And now it can generate goals. So just sort of given, I guess, Z sampled from some normal distribution, something like that, then you can use that to both like get the state that represents from that Z, and then this is actually the goal you can condition the policy on. And then from here, you can still use this generated goal as the thing that's provided to the policy as an image for it to be able to match. Okay. Does that make sense? Well, does this not seem like a slightly odd thing to do? So, okay, why is it odd? Mm-hmm. Yes. There's really a bunch of things wrong with this, or at least that could be improved. That's one of them. You can also kind of think about it sort of like if you were to watch or like if you happen to have 1 or 2 year old nephews or family members, like if that was the data you tried to train your own model on how to figure out how to do tasks, they're probably not going to like compete in the Olympics or figure out how to like program transformers. So the data set that's going to be collected there is going to be not so related. Uh, there's also an ugly truth to this one too, where I'll get into part of that example. One of the reasons why random data sets really don't work well, they don't interact with objects much. So often when we were like originally training some of these models for VAEs to generate goals, it would just be the robot arm moving around. It would never touch the objects in the scene because your random policy is not going to accidentally solve the task, even though that's like the goal we would eventually want the agent to perform. So this does make it tricky in order to sort of start from this and use these representations well. And that's a lot more where we've talked a bit in the class already about like the importance of being able to collect data, how it's hard. But usually to get like good representations, you kind of need to solve the task beforehand, or at least have some data for it. So that becomes at least somewhat challenging. Okay. I will faithfully try and play this video and see what happens. Can't play this video. Okay, end of playback. That was risky. Okay, still works. No problem though. We can always go to the web page, and this one doesn't go to YouTube, so I'm less worried. But this was some of the work that Vici was working on. And the idea is like you can just now take a robot arm. They collected a lot more data than just like a simple random policy. So they like we had the idea beforehand that, just a little bit of random data doesn't function too well. But sort of the same concept. We're here, trying to figure out how to command an agent to be able to take a particular goal, collect a bunch of data samples. Even in this case, this was sort of a bit before offline RL, but you could extract a bit of a Q function from this. But the part here I'm really trying to get to is this imagine goals pipeline. We're here, so these are some experiments where like the top image, the robot sets its own goal. So it's a little fuzzy. That's partly because like the VAE isn't capturing like the sharpness of the image really well. Whether or not that's in the encoder or the decoder, hard to tell. But then in practice, you can basically now provide this as a goal to the agent. And, it looks like at least the robot arm is trying to reach the fuzzy approximated version of what's up on top, right? Do most people believe that? At least it's not just me. Okay, great. Um, and then the nice part is, and really part of the goal for this now is you can just take an image of what, is desired for the robot to actually be able to be perform, provide that image to the actual robot, and then we'll figure out how to get from its current state to the state that's in that goal image. And now we don't have to worry about kind of messing around with goal distributions, figuring out how the state would represent the actual goal. So this is almost kind of like an advantage for human robot interaction here, because instead of having to understand like the pose for the robot to do a task, here's an image of what you want. People understand images much better. So it's much easier to do tasks. And I suppose also if you're a fantastic artist, you could try and draw your own image for something like this too. I'm not an artist, so I just take pictures of robots and post them on the internet instead. It does work as well for some objects to be able to match this as well. So if you provide some goal locations for things to do, here we're trying to get it to focus on moving this particular bowl around so that it pays more attention. Um, this, yeah, also had a bit of that caveat where do you kind of notice how large the bowl is? I'll just say that's important. It has to take up a kind of sufficient amount of pixels or pixel density in the image so that the latent representation has to pick up on this. So when you try small objects, generally it'll be hard for like any machine learning system, even if you start from like convolutional neural networks from scratch, small objects are difficult. So if you want to make your life easier for evaluating your algorithm that's doing RL or control and not its ability to do perception, pick some larger objects, worry about smaller objects later. Okay. And that's sort of, there's definitely a lot of future directions for this as well. Okay. Any questions about this? Yeah. Yeah, you could. That's actually one of it's a partial advantage of this method. It will be one of the papers we talk about later. Because now there's maybe an easier way to provide subgoals. And now you can give them as a bunch of images or just take a video and pull out some random frames in that and then actually have the agent learn how to follow those. There's a lot more detail to that though, like how to figure out what goals to pick to give to the agent. It's a very challenging problem. That was even a bit, did we talk about that when we talked about the high robot last week? Where like now there's maybe a high level policy that we'll get to maybe by the end of the class that's trying to figure out now what are the best goals to give to this goal conditioned agent for it to solve my high level task much faster or even at all. So that's picking sub goals is really its own reinforcement learning problem. Yeah. Although I don't want to sound like a broken record. Not everything is a reinforcement learning problem, but most things are. Um, yeah, and then can you evaluate the goals provided by the user? I'm not going to be clicking on videos, it seems this year. I guess maybe this PDF reader updated and doesn't support videos as well as it did last time. That's okay. Right. So a little bit of practical notes for whenever you're doing this, or really when you train any representation. What's going on? Okay. Hmm, technology problems seem to like to plague me. A bit for your patience. Fantastic. All right. Well, I solved this last time by going to grab it from the class. So there's definitely a couple of practical, well, ways to make this easier in your life, at least. So one is that you can actually reuse some of the other chunks um, from the VAE. So let me at least go teaching, learning from this year. Okay. Hmm. All right, back down to where we were. Okay, practical challenges, and it looks like technology works again. Still working on that humanoid human computer interface problem. Um, so the policy often ends up using the encoder. So actually, as much as it looked like, at least in the original code, like as input, the robot or agent would take like the original image as the state and the original image as the goal. It's much easier to actually use the encoder. So for the VAE, there's the encoder. So encode the image and the goal, the state image and the goal image. There's a lower dimensional representation for the state. That saves you some time, certainly some compute. Um, okay, so one of the nicer parts for now is that this encoder, we can still use it to compute reward distances. So there was a bit of, maybe you were all really worried at the time, like, but Glenn, how do you compute rewards now that you've trained a VAE model? If this is done well enough, basically the rewards are now computed just by like compute mean squared error between the latent representation for the current state and for the goal. That, at least in this representation, I'll put a little minus sign there, that's supposed to be there. That can still work well if the representation is trained well enough here. And that's going to be really common for a lot of representations. Short bit of information. This is maybe one of the harder things to get right because if you remember, like we've talked about how deep reinforcement learning, it likes at best, like if this is like the max reward that can get, and these are zero, it's your RL algorithm is going to work much better if there's a nice, smooth, dense reward that you can give it. But in this case, we're learning a VAE, and now this is a learned representation we're going to be using for this reward. So very often, the way this reward might look is, like something like this, if you're kind of unlucky, because the representation space, is not going to be perfectly conditioned to be really smooth. It can map to like all over the place. Maybe the max is still the same, but to be honest, it could be like have really like what do you call it? Like basically really high shape change around the area that is your state, which might deter your RL policy from being able to find that goal really well. So there's a lot of, let's just say a lot of work, time, and tears will go into being able to learn this representation such that it works pretty well. What I've found works out pretty well is surprisingly making the representation enormous. So something like 512 or 124, which is way beyond the pose for the robot or the object. It seems that at that point, the representation just kind of looks like one big giant binary operation where like things are here and that's on. At least that's what was discovered through many, many experiments. Okay. Does that make sense? Yeah. Because now what we're going to get into a little bit more is figuring out how to learn these representations such that they can be a bit more smooth. Um, yeah, do the same thing. So during testing, though, you can just take in like G here will be some image from someone else, and this will still produce like the Z that you want to be able to learn. Target. Yes. Yeah, I would like to be able to have more positive things to say about that. But the question is about like figuring out, is there some study of like trying to understand these representations and how they're learned better? There isn't a lot. This is kind of gets slightly into the area of looking at like interpretability for machine learning. But unfortunately, the short answer to your problem is there's not enough data most of the times to train these models to get a good representation. I mean, we've talked about in like the talk for Carl on Wednesday that really in the robotics space, there's very little data. So you don't get the best representations when those models are ever trained. So there's kind of like before we'd even try and unpack our tools from the interpretability community, most likely half of this representation is just going to be noise. So it's just going to look like a bunch of noise, a teeny bit of signal, which is not a good recipe for training an RL policy. So maybe we'll get there at some point. Uh, there's maybe a bit of work on this. I've got a few friends that do causal reinforcement learning. They at least try to learn latent factors, but they use a different recipe for learning a representation that they know is going to be causal, not just like using a VAE on it and then hoping that you've got enough coverage of your data. Okay. Hmm. Yes, you could. So like in this case, like from the representation, maybe you can do like PCA, principal component analysis over, I suppose you do this over the whole data set to see what Z values you get out of your encoder, see which ones just look like noise. Although that's kind of bad because that means they're noise and maybe not part of the state. So it's kind of hard to use like statistical tools over this particular representation because it's trained to match a normal distribution. So it should have a bunch of noise. We just don't know if it's properly correlated with the inputs and like the representations we want in the actual environment. Yeah. I'm going to get to a few causal things. Well, a few versions of hinting at like maybe we can learn something that's a bit more useful. So let me try one or two of those. Yeah, okay. We already covered this. This representation is usually far from perfect. I guess short story. I mean, if we had the perfect representation here, we could all go home. Like figuring out a good representation is often most of the machine learning problem. Once you can find good distances, like in any state space that corresponds to your task, you can just put like any planning algorithm on it. But being able to collect the data and learn the representation is a big chunk of the challenge. So this is why I mean, it's kind of why like Aaron Corval teaches a whole class in representation learning, and it's still going to be an open area of research for a long time. Um, right, so you can still generate goals from VAEs. This is nice rather than random goals. This can still be sensitive to background noise. And this is a bit of a challenge because we want these agents to be really taskable. Like if the goal is given to them, they should be able to complete that goal. Um, and the idea is to get them to really do this independent of situation, but sometimes that demand for like totally independent of situation is much higher than we think it is. Uh, so I'll give an example. So like if we want the agent to focus on some task relevant part of the state here. So think of in this case, like here, this is only like make the plate table setting look good. But there's a lot of other things to potentially consider. Okay. One of these is that the background or fireworks usually really sensitive to prior noise and doesn't handle diversity well. So I'll give a particular example here. How can I do this? Oh, sorry. There's usually a lot of things that are going to be noise that aren't. Okay, so we talked about noise and the fact that we want to be able to generate tasks. There's also some ways it's better to generate goals that the agent is going to be able to achieve, but that usually means two things. So one, which I'll give in this example, is sometimes there are different objects. Like often there are very many different objects. You can't have all of the objects in front of the robot at the same time. So at least in a version of the prior work, like if we trained a VAE or some model over all that data to generate goals, it's going to include images for a bunch of different objects that are in front of the robot. And now if we use the system just to generate some random image from the data set, it might generate something that is an object that's not currently in front of the robot. It's this version of like figuring out, oh, there's maybe more conditions to be concerned with. Luckily, one of the short answers we can try to do here is, well, now it seems like goal generation should now be dependent a bit more on what the configuration in front of the agent. So at least it can generate something it can do. And this is really what we can do in this process, and at least a bit of other work. So we need a bit more information. So here, what was done in some other prior work is now you've got two inputs to the actual VAE. One is always like the initial state at the beginning of the episode. So this information really just provides what is the color of the arm, color of the table, what do the objects actually look like that are in front of the robot. And then now this other chunk for the VAE is the state. So now this is, well, it's the state in order to provide the input, but the really important part is to figure out, well, now you can use this for goal generation. So now the VAE is trained over, like here is an image of the initial state and an image of how like the data is unrolled from the actual episode, and now generate just images from that episode based on this initial state information. So it's this kind of, it's a context conditioned VAE where the context is really this initial image that at least gives some prior on what is available for the robot to interact with. And then use that instead to generate images. So then when we get down into uh, this case, now basically for some initial state, now our model will only generate things with this white giant puck in front of it instead of any of the other random items that were in the data set. Okay. Does that make sense so far? Part of these tools are really nice too, because as much as we've talked about collecting data, at some point it'd be really nice to get back to using generative models to generate data for our robotics data sets or deep RL data sets too, in order to be able to kind of like, modify or augment that data. So we don't have to collect data for every single random thing and every single random object and color for it to actually work. We should just hopefully generate some data for that and only maybe do the dynamics collection once and then have all the other data that's just like appearance modification for what's in the scene. Okay. Okay, does this model make sense? Any questions? Okay, the only slightly odd thing that we do in this model that at least we haven't talked about too much is we do apply a little bit of an information bottleneck just to make sure that not too much, basically that there's not a lot of information contained inside of the Z vector that's used to describe the state. So like it should focus most of its attention on this bottom image. And then really the other latent representation should be like a modification of that image, just to make sure that it focuses on that initial image and doesn't ignore it, which it did a lot when we were doing this project. So the information bottleneck just literally kind of based on the word information tries to reduce the number of bits of information that are going to be available and passed through this other kind of avenue instead of this one. So here is kind of a bottleneck that forces it to not contain all the information. One way to kind of balance your representations. Okay. Questions? Good. All right. So that worked well. Again, nice part about doing some of this research, it's a very easy change. All the other algorithm exactly the same. Now our generation for new goals just also depends on S0 and not just everything. All right. How are we doing? All right. Okay, no, perfect time to take a break. So let's take a break right here before I get into how I've not lied to everyone so far, but let's just say goals are actually very inflexible and not easy to use. And then afterwards, we'll get into the reasons why we need to figure out how to do different representations entirely than just an individual state. But for the moment, let's take a break for a little bit. We'll start again at 2:02. So in the meantime, I'll get this. Oh. Hmm. 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 Okay. Hmm. Oh well. How's everybody doing? We can get started again, and I could spend this time not having to worry about the challenges of being able to purchase robot hardware at the moment. I bought a mobile robot with arms, but I'm only allowed to purchase either robots that are mobile or robots with arms. So they're giving me a small hard time about deciding which one of these particular robots is actually a robot with arms or just a mobile robot. But whatever. Okay. No problem. Um, all right. So then in this, so we already started talking about some of the challenges with goals as images. And I know this is kind of leading towards our discussion for like why images still aren't great and we may want to use language. But all right, the image on the top is not an image of my room. Don't worry, it never gets that messy. And the image at the bottom is the goal. That's like the clean room that hopefully we want the robot to actually be able to perform. I guess my question is, if this was given to a robot, what are we really telling the robot to perform in these two images? Sorry? Hide everything? Hmm, it's not bad. It's a good example. So, but what do you mean by hide everything? Why is that bad? Sound like you have some experience with this. Maybe we all do. Yeah, because what do you think? I'm the one posting this image, but what do you think is really intended that we want the robot to do here? Yeah, and then like clean means like organize, have a nice home for everything, so you can find stuff later. So images can at least be somewhat, deceiving and not really specifying the task. Yes, kind of. And we'll get to like, so there's this balance between what's going to like text-based goals versus image-based goals. So in one ways, it's harder to describe what is really meant when an image is used. At least, like I said, I'm also not an artist, so that's not perfect either. One of the challenges with using text-based goals is they tend to underspecify the task. Because you could, I'm sure, I'm not really pointing any fingers, but when our parents or whoever would tell us clean the room, you could still stick everything underneath the bed, right? That's still a possible interpretation for that idea. I want to get to one other really weird thing that we may not understand that we're actually telling the robot to do here, because the idea was like, this is now going to be some latent representation somewhere, and then the idea is to have the agent move the entire state to that latent representation. So there's a window in this room. What are we telling the robot to do to everything outside of this window? Sorry, change the time? Yeah. I mean, remember, like the robot is not smart. It doesn't really understand intentions. If you were to think a little bit far through this, the robot is being commanded to reverse time. Whatever is outside of that window, put it all back in place. If there are people out there, I don't know, kids playing in the park, a bunch of people having like fried chicken and wine or something in the park too, the robot needs to make that happen. But again, that is not what is meant by this picture, but it is what is technically told to the robot by everything we've described so far in today's lecture. So, not a good idea. Probably not, anyway. I mean, if it can turn back time, I would absolutely do that just to be able to have that ability. I'd probably go on vacation or something like that. And then my next class, I'd probably look 10 years older, but you wouldn't have to worry about that right now. So we need to think a bit carefully too, even before we get to representations. What are the easier ways to be able to specify these problems and make sure we're specifying them in like a proper way and ignoring things that we don't care about. So this is where, okay, for image-based stuff, most of the time, the task is over-specified. Like make every pixel look exactly the same. And that's why if you look carefully for like some of these papers for robotics, they'll usually put like a curtain over windows and things like that. It's not to really avoid the outside. In that case, it's more to like prevent lighting changes from messing up your data distribution. But it does also prevent this kind of scary use case where it could maybe try and turn back time. Okay, so let's talk about this and what is now meant a little bit more by these representations. And I'll go through this a little bit quick so we can just get to the details. But at least part of the problem with that image-based part and why we fundamentally kind of why we eventually want text-based goals has to deal with this issue. So it's really what we want to really do is specify something to the policy that isn't an individual state. It's something that can represent the task much better to describe it and how it should be performed. And one way to start for doing this is what I'm going to describe as just like distribution condition goals. So this isn't an individual state in this case. So I'll skip a few of these chunks, but basically goal condition reinforcement learning. Uh, Maybe I'll play this so I can draw. It's still always goal state, but that assumes we care about every single thing in that individual representation. But would everyone at least agree that, put the red block in the box for every picture on the left satisfies that goal? And actually, there's a bunch of different states here that satisfy that goal. So, okay, if there's a bunch of different states that satisfy that goal, and there could be a number of other arbitrary behaviors, that means this is a distribution, and we need to figure out how to just describe that distribution well of like some of the features of the actual state needs to stay the same, but these other ones we kind of don't care about, and you can essentially sample from that. So then with that description now, like the kind of maybe somewhat natural next steps is to maybe construct a distribution instead of an individual goal state. Does that make sense? It's not too weird? Okay. And this is really partly, like language models are trying to do this in a much more complicated way, but let's kind of talk about the fundamentals of like why we want that type of representation. So we basically want to make an algorithm where we can, infer reward functions fast and still have that general purpose taskable agent. So kind of short story to this is goal distributions. You put a red block in a box. This is now some of the actual state features are like desired to be pretty much the same. Some other ones don't matter as much. And for here, this one's actually kind of tricky too. If you didn't notice this one, like this is still a red block in the box. This is also red block in the box, but the box is in a different location. It still meets the original description. It's really hard to actually figure out how to describe goals properly. We'll probably be doing this for a couple of more years at least as we start to get better at it. But here we've got a small data set on the left. It was a bit auto-generated, but now we can just like fit a Gaussian distribution over the state space for all of the stuff that's on the left. And now if we've got this distribution, this is really just the X position for the block and the box position. So those should be similar because we just really care about having the block and the box location to be the same. The other stuff we don't care about as much. And now take the parameters that describe this distribution and now basically train the policy over these parameters. Now that you can create a goal condition distribution over these individual like understandings for different representations. Okay, does that make sense? I want to make sure this is kind of clear because once we start getting into like, okay, we should just use text. What type of representation do we actually want when we're going to train a policy over a bunch of different outputs from some language model kind of at random, but we want certain types of properties over these distributions in the future to make sure we're capturing like everything that the robot might be asked to do. It's actually quite a broad thing, takes a little bit of thought. So, any other questions? You were slightly faster. Hmm. You don't always need a camera. Like yeah, at least for the examples here in this, I know I'm showing an image, but we use like the state space for the actual simulation, just so we could sample it well. But I would at least hope it's a slightly different problem to do this and have it at least be robust to viewpoint. At least I would hope, and fundamentally, there's still the same state features described in the overall problem, even if the picture is taken from different locations. And I'll kind of make a few assumptions there that still captures like all the blocks and everything and still works well. So those are two slightly different representation problems. One is just being able to capture from image to the proper state description. And now the second problem is actually the task is a distribution, not a state, even over those state features. Okay. Other questions? Okay. Now's your time to ask questions. All right. So, all right. Obtaining the parameters, at least in this case, not too difficult, and also something we might be a bit familiar with. So the idea here is you have some data set. Maybe if you're at least vaguely familiar, or sorry, this starts to look like in-context learning. Like if you want to describe what the task is, provide a couple of examples where that task is correct. Train a model to then basically go from this in particular distribution and then infer some actual like embedding from that, and that becomes a description of the task. And sometimes like giving more data to help describe this distribution makes the policy work better and better. So really the same behavior here. Provide a short collection of basically examples that describe what the task should be. And for some distribution, here we were like in the glory days, I don't know, of reinforcement learning or something. So this was in some cases just a normal distribution. It wasn't an entire language model, but the idea is this thing in the middle is now can be a lot of different things. People are using language models for this. People are using in-context learning for this. Some people are even using like video generation models because you can feed in the context for a little clip of video and then generate a whole bunch more of the video. That's also like an example of this problem. But I'm trying to say that like almost a vast majority of things we're trying to do in robotics right now is we've got what's on the left. There's some challenge of figuring out how to both represent and describe the task, which is now this ugly thing in the middle. And then really the run disco RL is just like run RL on this problem after you have described your task properly and gotten the right representation. Here, we can be way more sample efficient just by assuming some structure in the representations. Hopefully that makes sense, right? It's also one of the reasons why I really like this paper. I've got a few of these. It's like, we're still doing this, but the thing in the middle is now a trillion parameters and takes forever to train. The thing on the right is now just run for much longer and more diverse tasks and problems. And the thing on the left is, well, we're still trying to collect data for robotics. So we're kind of low there too. So we're making some progress on each of these three main points of kind of like the RL and robotics pipeline. But then at least to go over some of the details for this. So now policy is conditioned on these parameters, or you can think of this as some embedding vector, whatever you want to call it for now. And we'll get into some examples for that after this is over. And then this is your reward function, like increase the log likelihood such that, you know, the state that the agent is in has really high likelihood under that distribution. That's it. Nothing real complicated about that. Find the highest peak in the generative like distribution for that distribution you've learned. You can maybe think of like this is kind of what in-context learning is trying to do as well. Okay. All right. And now the rest of these slides look over kind of quick. This is more like stuff we've talked about in RL, but they end up, you know, helping this train a bit faster. So do off policy RL because we've got some data that we already use to train this model, some data that we use to also train to get kind of like these parameters. So the nice part is at least in our case, we've got some implicit model for the reward, so we can go back and relabel data. If you remember hindsight experience replay, the question is, how do you do hindsight experience replay now when you've got a distribution instead of a goal? So you can't just label the last state in the trajectory one reward because you got to that goal, because now it's a distribution. It's a bit uglier. Short answer to this story, if it's a Gaussian distribution, you can just put the that last state as the mean in that distribution. That tends to work pretty well. We never really found a good solution for like in general distributions figuring out how to do this relabeling well. We tried a few methods, couple of different distributions, tried a couple of different environments, and some algorithms worked a little bit better than others. But I think the part I want to be able to get to is not in this particular paper. Anyway, let's go way back. We tried the process of being able to relabel the actual variance as well. It didn't seem to help. The mean was much more important. You can try a bunch of different environments. I'll go over that part and a couple of different algorithms because this was sort of back in the time where goal conditioned RL was also still kind of forming, at least in a more complicated space. So you could, I don't know, VAEs is this, like one way you could learn a reward function is train a whole deep network model to predict for some particular reward, and then condition your entire policy network on the parameters that describe that reward function. I don't recommend doing this, but it does seem to be what we are doing these days when we're using language models because of the amount of kind of what's being crammed into that representation. But that's like one of the methods to compare to. Anyway, here lower is better because we want the agent to find, like be close to the target goals in this. So kind of inversely rewards. Here we're looking at distance instead of rewards. So it does much better. You can describe more tasks with it given some distribution here. Even if like the box is in different locations, even if the initial configuration in the environment starts out with the blocks in different locations, doesn't matter. Hopefully we'll ignore all the other blocks and just do the most direct solution for the task. Can you speak a bit louder just over the air conditioner? Can kind of hear you. Hmm. Uh, it is similar. Like, so mathematically, I would say it's the same. The only real difference is if you're like, I think you're asking like if you train a model to be the reward function, or like for a language model that spits out a large embedding. Really, that's just the size and number of parameters that change quite significantly. If it's, if you, at least in the vice case on the top, for it to be mathematically equivalent, you'd give the parameters for the entire network that describes that reward function. So it just doesn't generalize well, like how much smooth shaped structure exists inside of that representation for describing reward functions. Does that make more sense, or was that not quite your question? It's a really, if that's what you're wondering about, is like how, like in this mathematics, like in this framework here, like the omega parameters are basically something that we essentially trained in order to match that distribution of initial data. We just treat it as just like a Gaussian distribution. You could use much more complicated functions in order to be able to fit that data, including like train an entire deep network to be able to model that distribution. Then this can either be, it could be our normal distribution. Um, it could be an entire deep network that basically models reward of S given A. It could also be some LLM, embedding that takes in the text that describes it and then produces an embedding. I think we were conditioning on the whole parameters. We still only trained like four reward functions. So I wouldn't say we were being unfair. We were following the details of how we'd compare to it, but it's particularly terrible to try to compare device. Like, yeah, it's a binary classifier, kind of like, I don't know. The stuff that's inferred, these are basically the positive examples. So you'd label them one and then sample a bunch of other stuff from the data set that would be zero, and then train your binary classifier to do that. So this is it's how you could use Vice, and it's how we did use Vice in this case. So Vice isn't really designed, uh, like it's not designed for this sort of like generalization part as well. That's why I kind of need to put a bit more thought into, okay, now what still makes a good compact version of this representation, but that won't require too many samples for your policy to then learn how to generalize, maybe interpolate a little bit across the different spaces of goal representation. Because like here, the network doesn't really care or know that this is now a distribution instead of a goal state. It's just some parameters. Sure, the learning, not the learning dynamics, but like the learning surface is going to look a little different. But we really didn't change anything about like the goal conditioned RL code except for add twice as many parameters for the mean and then the variance. That's the difference. Yeah, for Vice, this was like 50,000 parameters and then like 10 samples or something like that. So it wasn't really a fair fight in that case. And then in these days, we're using like treat a language model, have that output a goal, use that embedding here instead. But that's actually could be a really ugly like representation space, very unsmooth. Who knows how well it is actually to interpolate between these things. That I think we're also still getting to the, I don't know, early stages of being able to understand how that works and improve on it. Okay. And this is, yeah, we tried a few other models. The stuff on the right was really hard to use, kind of because we went down the rabbit hole a little bit to make it more fair. But now for like our in-context data set to be able to do a mixture of Gaussian models, we could use maybe 10, n equals 10 samples here. We needed at minimum 1,000 for like a mixture of 2 or 3 Gaussians. And then this is, again, our old friend, like train a VAE to sort of understand a general distribution, or, these days, train a language model or a vision language model to understand this. And hopefully the representation has got some smoothness to it. It's something that eventually the policy can figure out how to generalize over. But I say we're still struggling to do that at the moment, probably because of data limitations like Carl was talking about. We've got really little diversity over tasks. And that's really what we're talking about here is representations over task descriptions, not just like perception of the, I don't know, the block is blue instead of green, something like that. Okay, good. More questions? Okay. Yeah, so the rest of this is, yeah, there's some examples, some environments. This is the one, so we can also use images to be able to train a representation. Like I said, lower is better. And this was the comparison device, which is, it was like the closest baseline that technically followed some similar mathematics, but was not going to end up working out too well. Um, right, and this is the part that I wanted to get into a bit here. Uh, Specify some example set for a goal distribution, run RL. There's also this conditioned version. Okay, so now this goes back into how to generate goals. So we're basically trying to recreate this whole like goal conditioned RL pipeline, where originally we're talking about, well, now we can generate goals from a VAE. Now we need to figure out how to generate distributions of goals in order to be able to use those to sample. I'll just say it was kind of painful. But now the idea is given some state in the goal state, this is train some conditional distribution that generates some state between the current one and the final goal. And then generate, so this is now like a trained distribution that generates sample goals. And then we can compute like a small normal distribution over these sampled goals and say that's like a sub goal on the way to the final goal in order to be able to have it generate goals. And this is now the other thing that essentially people are trying to do these days. So people now are using like language models instead here. So like given a final goal, please language model, give me some fantastic sub goals between this goal and the final goal in order to be able to get to that goal easier, or generate goals that are going to be more likely for the policy to be able to be solved. It's still the same mathematics, but like you've got the initial state, you've got some data distribution you've trained over, and the problem is like given some final goal, what should be the thing to generate such that the agent will follow along those sub goals and still get to the final goal. Still the same problem. We're just using much larger models for these days. And then you can train over these distributions, and then can conditioned Disco solve longer horizon problems now that it can generate goals over these different distributions. So it can do a pretty good job at being able to do Sawyer manipulation. The one, like the whole reason, to be honest, we wrote this paper is to be able to do this IKEA experiment, because maybe you also hate assembling IKEA furniture as much as me, but the real thing is in most cases, many of the steps in solving like the IKEA assembly problem can be done in any order. And depending on that conditioned configuration in the beginning, then there's an optimal order. But this one is also particularly, at least interesting for me, and I'm just gonna like skip this whole thing because I no longer care about it. It does better, let's just say that. But if you really have a piece of IKEA furniture, and hopefully this doesn't mess with minds people's too much after we've talked about all these states, let's say you're constructing this shelf and all of these boxes on this shelf, they are identical. It should not matter where you place these objects on this shelf, right? Just like if you were to assemble like a table and all of the legs for the table are identical, it doesn't matter where they go on the table. It shouldn't matter anyway. But for everything we've talked about today, it would still be, like there's going to be this state has to match. So it's going to force in the beginning before the like episode even starts that no, this leg has to actually go to this particular corner of the table, just by the way we've kind of described the mathematical framework so far. And that is not good. like to put it shortly. It's certainly going to make it such that, well, now not only is the agent being told to solve a task, it's being told to solve it in a very restricted way that could also be non-optimal. And the reason we were doing those like conditional distributions is now it's like, okay, now give us the initial state, give us the final problem, kind of relax the constraints that like particular legs have to go to particular spots, and now just generate basically a sequence of steps using what's available in order to be able to get some leg attached to some table within some amount of time, and then you're done. Because like most problems, order is flexible and a lot of items are interchangeable. And this is partly what we're still wrestling with. This is really one of the reasons why using language models and text ends up being pretty helpful, because it's not going to really describe in the representation, like put all four legs on the table. It really shouldn't capture the part of like which legs in which order at which exact locations on the table. That really doesn't matter. But a lot of the annoying parts of machine learning is actually we're trying to deal with this problem, is that there's some distribution of possible solutions. We're happy with any one of these. But many of our mathematical frameworks force one from the beginning that it has to meet. Okay, does that make sense? These are things you probably don't even think about because they kind of come natural to you. But to be honest, in the machine learning algorithms, they're kind of constrained to these annoying solutions. Yeah. Um, hmm. I think, yeah, this one was image-based. Half of these were image-based here. The image-based part helps a little bit in terms of capturing some of the representation. It was still pretty hard to get the VAE to do what we wanted to do and capture a nice representation such that it would do this. So maybe that's a whole nother reason why you should get away from images. Getting that representation is not actually that easy. Yeah.
Was the goal condition distribution also conditioned on like
Yeah, I think that's right. Here, because if you go back a bit somewhere too far, because it was S of like S final given current S, something like that. Given final state, generate a particular state. I don't remember that exact detail, but that would be a good point. Although I think in this was kind of like generate the sub goals at the first state of the episode and then try to meet all those sub goals. They don't change during the episode. Yeah. Okay. But you could definitely, I know in some of the newer methods, it's good to be able to adapt. Like even if some people saw like Gemini's new robotics demo where they move stuff around in the scene, it's probably querying itself to like figure out, okay, should the goal change because maybe the scene changed a bit. So here we didn't have to worry about that because we didn't have any annoying people come along and change stuff about the scene. But it's good to be a bit more closed loop and adapt. Okay. I think I now just want to like try to skip through the rest of this and get right to the point. And now we can get talking to a little bit more about language. Okay, give me 1 second. Okay, this is the correct slides. If you're on the proper number of slides, if after the distribution conditioned RL, it does not say whatever, scratch. There's actually another 10 slides after this where we get to talk about language models. Okay. So this, after we get through this process, and now we talked about the concept of what's good for these distribution condition models. And now we can basically try to use these like language models for these instead. There's still a bit of a challenge on like how to train a good language model. So there are some big models, and doing a good language model, I guess this should also say like for robotics, where there isn't nearly as much data. There are some really large models out there that can do a kind of good job at capturing some additional data and being able to train well. The challenge is like if we wanted to use something like the models for Gato and BC0, they're actually pretty slow. Like even Gato is enormous. I know we haven't talked about it a lot. It was mostly used for RL, but it was still imitation learning. So those wouldn't work really well for the small data sets that we had and kind of still have for robotics. So we need something out of these. It's a bit of a trade-off such that it doesn't need as much data and can still condition well for language. Um, one of like the nice versions of these, just as an example, is the perceiver actor paper. So in this case, it's not a really large model. It's part of it was pre-trained because it's using this perceiver IO transformer. But here, this is trained with not much robotics data. I think there was something like it's still using simulation. So maybe like 10,000 frames and then like 50 trajectories on the actual real robot. But it does condition this particular language input now. So now it's the goal now is actually from the language. There's no image-based goal. There is a state where the state is actually a bit interesting here. So instead of using an image into the scene, it voxelizes the entire 3D scene. So it's huge in terms of input. But now the goal is just this text. And then this can be trained over, just like a couple of hundred, a couple of thousand trajectories to then be able to generalize to at test time some slightly different specifications for this goal language. So this really didn't use much pre-trained language models yet, but this is one way or one place to start. Um, if you want more details for this too, you can go and see this person actually gave a talk in our like robot learning seminar last year. So it's even more details about how this actually works if you want to know them. One of the part that's maybe it still helps, but as a bit of a thing to point out is like the diversity over the goal specifications in text, still pretty simple. You can almost say that this is like, X verb Y, and that's like consisted of all the representation of all the sentences in the data set looked like that. So it would be like X put on Y, something like that, or X put next to. So there wasn't a lot of diversity. So it didn't need like a giant LLM yet in order to be able to solve those tasks. It could just figure out kind of this two object relationship text understanding on the overall data set, and then it would still work pretty well. Yeah. Um, I mean, the perceiver IO transformer, I think, works pretty good at processing image data well. I think in this case, it was also to avoid occlusions, because then when the object and the arm would move around, and if it blocked the object in like the middle of an episode, the arm would no longer know what to do, because it's like the goal is hidden behind the actual arm. There are future versions of this where then they stop using the voxelization, but they do use like three different camera angles, like from the top and from the two sides, which pretty much eliminates occlusions. So because they did that, makes me think this is mostly for occlusion. There's definitely no occlusions here, although it's still pretty coarsely sampled voxelization. Yeah. Okay. So this was a good start as one of like the methods I was starting to use in language as goal conditioning. But there's still, okay, but then there's kind of like the other side of this. We can basically either start from scratch, make our own like foundational models for robotics, train them with only robotics data, or we can start from a language model or a VLM. These both have their own caveats and problems. The one where we're starting with a language model that's more of an LLM is the challenge is now they lacked grounding. So like that perceiver actor like did a voxelization of the world. It knows like when anything changes inside of that. So it gets a pretty good understanding of how things move around like, from the data it collects. But, in a language model, it doesn't understand really what is fundamental to grounding. Um, do people know what I mean by grounding? Kind of. Okay, good, because I don't think anyone in the community actually knows what they mean when they say the word grounding. But I think it's at least helpful to give a few examples. So if you kind of know what it is, do you want to give me an example of like grounding or not grounding?
There may be something when you ask your policy. Yeah, let's say clean up your room, and your policy doesn't really know what it's about. You have to ask it. Just look at the name of it.
Mhm.
Not grounded, but
Yeah. It's not even grounded to what a room is. Like a room is a symbol. It's some vector inside of the space. But if I was, like to think about like a room has a use in many cases, it's usually confined in some space. So at least like, when it says like clean, that's also got a lot of ideas and concepts around it. It's not just shove everything underneath your bed. It's to be able to like actually put things away. So the LLM gets tons of this information as symbols, but it may be lacking some of this information about like the dynamics for understanding for like what these mean in a physical world where we want to do stuff. And that usually provides some like intention about how they're being used. There's often still sometimes a bit of this information in an LLM. You could probably ask it, well, what do I mean by clean and what do I mean by room? And it might give you some info that it read from other people and not in this class that think more about cleaning rooms. But it's also down at some other levels, it becomes tricky too, like understanding dynamics. Like, what does it mean to clean? Does it mean like moving around? Do you actually have to vacuum the carpet? Do you have to worry about every bit of dust that actually exists inside of the room? Kind of depends on people's preferences. So, but I also want to make sure we get through this. So, one part that can help, because the idea is it's also, we don't know what's possible. So one way to interpret this, like if you don't know what's in the room, if you don't know what objects are available, well, one of the, not cheat codes, but things we're used to doing is one way to do this is, well, now if the LLM is going to suggest goals, because just remember we're talking about goals today, the goal it suggests should depend on how good the like goal condition policy is at satisfying that goal. It's like one form of grounding, like filter its suggestions by things it can actually achieve. Like I don't know. Hopefully no one ever tells me to like go play basketball because I'm terrible at it. My Q function is very low in that space. Instead, it should be, I don't know, giving lectures or something like that. Sure, I'm okay at that stuff. But then, so this is what the work in SayCan does as a version of this, where SayCan is there's some policy where there's our like the original goal, clean the room or like go grab a bag of chips, something like that. And the challenging part is to figure out, okay, what sub goals should this generate now in order to be able to eventually satisfy that overall goal. And now these sub goals basically can use the Q function as a filter because now they've got this other model that takes in sub goals. And if it has a really low Q value, like over any action it could take from that state, it's probably not a good goal. Maybe try some other goal, see if it can sample this process to be able to find a sequence of sub goals that overall have pretty high Q value. Then it's likely they'll be achievable according to at least the grounding for that policy. Okay. Does that make sense? I feel like this is also something like when you work with someone else on a project, you kind of get used to their Q function. Like you want to give them tasks they're excited about, things that they're good at. So you kind of work together to figure out and trade off goals. Okay. All right. Saycan worked pretty well, but one of the at least components for it is it used a very custom goal condition policy. So this particular policy, really hard to achieve. It's very fortunate to be at places like Google where they can assign 10 to 20 engineers to spend their time training a policy that takes goal text and tries to satisfy those goals. But it'd be much better if we can find a more scalable solution for this. So this is where Saycan was using this goal conditioned policy to be able to act over these sub goals. And the performance of Saycan, like that thing that was trying to satisfy high level goals, depends a lot on the abilities of that lower level policy, that Q function here and what it can actually do. So if the point is to be able to improve, these policies that are being able to reach like the overall high level goal, one way, make a policy of more like lower level one that can satisfy many more goals with like much higher likelihood, much better Q values. Makes sense, right? It's sort of, I guess it's the reason also why like you practice things, you go to the gym, you work on your math. So if someone gives you a problem or some sort of weird sport, you're like prepared in order to be able to do well on that thing. no matter what it is. So this is like more like the fundamental reasoning for why like the robotics transformer was made. In this case, this is now train like another version, not quite per act. This is now more complicated with a larger model and a transformer and a film layer. But the whole point of this was to be able to make a more scalable version of that like kind of hard coded, hard trained lower level policy for SACAN. Now there's this big giant transformer where we can feed in lots of data, lots of goals, train it to be able to satisfy all those goals. And then one of the kind of bonuses of this paper was to show that like now like using this particular model inside of SACAN greatly increased like the success on the goal distribution that SACAN was being tested on. So makes it work much better overall. Does that make sense? Everyone's kind of following the logic here. Now there's kind of like two levels of stuff. I'm going to kind of go back and forth on improving either like the part that takes text goals and moves the joints or the part that takes the actual goal and figures out how to generate sub goals. They're both pretty strongly connected. Obviously, a bunch of the components matter. So this is like RT1 here, and then this is like the performance lost whenever these things are subtracted from the actual model. So without a transformer, loses a little bit of skill. Without a little bit of history that's being kept, it loses a bit of skill, particularly on distractors. The actions here don't seem to matter too much. Actually, they might seem to be a bit of a benefit. Using continuous actions, yeah, obviously seems to cause some issues. And then like some comparisons to Gato and BC0. So this is just a bit of an ablation. So at least these other components that help churn through the data the model is trained on certainly help improve performance overall. Okay. Any questions about the robotics transformer? Does that make sense? We're not going into detail here. We already did that for like the Disco RL paper to understand why we're going about this. Here, yeah, maybe these models are kind of all trained from scratch, so they don't have the best possible representation for language, but they do have better grounding. And that's good for the lower level. The lower level should be a pretty grounded policy. Okay. All right, so then just a bit on the limitations, because we kind of skipped one thing. Not that we skipped it, I avoided it because it's something that we don't have anymore when we're doing language. So the challenge with text is it lacks grounding. This is why it's really hard to kind of describe to some other person or some other machine, like exactly what to do when it's a physical task. So that is going to be a bit challenging to work with. There's certainly a lot of people and some good papers. In particular, I like this one. This is the Palm E paper. And what they do in this case is they do take a vision language model, but then they train it on a robotics data set to try and give it some grounding. And then actually the model becomes better at both answering random visual question answering tasks and robotics. So giving this model, giving it, but at least training it over some of this more grounded data helps it understand maybe how to answer those vision question answers better. So figuring out good ways to be able to combine these two, like the symbols and understanding and language and the grounding that's needed to really understand why, kind of like understanding where the language came from. Because like the physical world came before language was invented, and then we kind of make language to help us describe it easier and pass on our knowledge. So that helps. Okay, but now the one really painful aspect of using language models is we don't have this anymore. And all of the previous representations, we could learn a representation, compute a distance between representations. Great, we've got our reward function. Now we just have text. There's not really a way to like specify a goal to understand if the agent has cleaned the room. You now need to go and train some other model potentially to figure out, and that's the thing that determines whether or not the room is clean or not. So as much as we've got these language models and we're using text, we've kind of shifted a bit of our work to be able to use these representations, but now figuring out how to label these with rewards has become much more complicated. At the moment, you can't, with a few exceptions. Hmm. So, so yes, technically. Um, you have to remember that the part of the problem is, so you would need a text to image generation model, and then maybe you can feed that back into the image-based model that was computing rewards, and you can get a reward from that. I'll just say this is really hard to get working because the problem isn't that we can't like take some model that does images to text or some linking and like use that for state representation. The problem is we specify the goal in text, and now we need an image for the goal to be able to imagine that, not the stuff for the current state. So we need something to generate that representation at the end of the actual trajectory. And part of the challenging part is now just figuring out nice, smooth representation spaces because the goal might be specified in text in that case, which means maybe it's going to get some embedding from the model that's given to the policy. So it figures out how to understand what the goal is. And now it's going to have potentially a hard time figuring out how to interpolate between goals because the embedding space is really big. It's also going to have really odd like shape over time. So it's hard to understand the generalization. But yeah, one option would be use text to generate an image using some text to like image generation model and then feed that into one of the other models we talked about that takes an image and learns a goal. I suspect there's still going to be some challenges in that. It's kind of why maybe using vision language models, because they have a lot of this like intertwined understanding between text and images, may help. You still need something that generates goals in the future. So you need to use like everything else we talked about today, with one exception. I think we also like one of the reading papers for the class was that UniPy framework. That was like generate a video instead of a goal. So if you've got text, maybe it could be instead generate a video of how to go from this state to this final state and then do imitation learning instead. So there's a couple of options to use here. But for the most part, when we're using text, it gets more complicated to infer what the goal is. It was really nice before when we just had state and the goal is the same representation of the state, but then we have so many representational problems about specifying the task. Uh, any tasks? Okay. Any other questions? Okay. So that's all right. Great. So that's sort of a wrap on the stuff for goal conditioning, and we'll talk a little bit more about the ugly details of now if we have two levels, like a goal condition policy and one that's trying to figure out how to do goals, and now we're training those. And we'll start on that next week. Otherwise, have a good weekend. Feel free to ping me for questions on stuff related to the homework assignment. Not too late on Saturday night, Sunday. I probably won't answer those. But yeah, good luck. Take care, everybody.